great to be here. Good afternoon, ladies and gentlemen. I hope to keep you a little bit awake after this wonderful lunch break. And I'm so glad that Professor Udo Kagel from Rostock already gave a wonderful introduction on NFDI and the German research data management initiative, which are already active for almost 3 years now. And what I would like to bring you in this topics in the topic of the afternoon is that we are already using the research data management tools in chemistry in Germany. And I would like to bring you some best practice from our research. So in my research as chemist in Aachen, I'm doing work on bioinorganic chemistry and bioplastics. And so I will bring some examples from bioplastics because dealing with sustainability, I think this topic was quite fitting today. And then I will bring you some examples where we are using the actual research data management tools. And later on come also to the impulses we give to teaching here. So I think most of us know that we have a garbage problem, a plastic waste problem all over the world. I would say in every ocean there is garbage plastics. Even in the Arctic and the Antarctic regions there is plastics and microplastics. In us there is already microplastics, which is a problem. And the problem will increase. So if we look at the numbers of the global plastic production, it's increasing. And in the same step, the global plastic waste is also increasing. There are more and more initiatives, for example, the Ocean Cleanup Initiative, the Alliance to End Plastic Waste, and more and more and more. I could make a whole list of them. But the problem is really that most of the plastics which are producing can lie around in the end for many hundreds of years. So I think in more than 1,000 or 2,000 years, this will be known as a plastic age because of us will be mainly found plastics in the end. And I think this is really a problem because the plastics is coming back to us. So if you think about the microplastics, perhaps going back to these figures, sometimes the animals really eat the microplastics and then we are eating the fish, for example. And so all this is coming back into the nutrition chain. What can we do here? For several years now, there are bioplastics that have been developed in chemistry. And the term bioplastics is sometimes a little bit misleading because this is a large family of different materials. Originally, it was thought to save fossil fuels, and I think this is fossil resources. It's still a good idea, but it's also important to have degradability. And if you think about bioplastics, then you can think about 4 corners. So on the right-hand side, perhaps it's easier to show like this. On this side, you have the biodegradable side. Here is a non-biodegradable side. Here's a fossil-based side, and up here is a bio-based side. So the conventional plastics, what we use on the everyday life, like polyethylene, polypropylene, or PET, for example, for bottles and flasks, is on this side, this conventional plastics. But you can produce a lot of these plastics from biogenic resources, which means, for example, in Brazil, you can burn rainforest, then you can plant sugarcane, come to sugar, come to bioethanol, come to bioethylene, and in the end, you can produce biopolyethylene bags, so that we as Europeans here, for example, can say, well, we have a bioplastic bag. But in the end, the life cycle of this whole is really not good because you are burning the rainforest to plant more and more sugarcane. So this side of bioplastics, they are bio-based, but they are not biodegradable. So in the end, this PE and PP will lie around as the normal conventional plastics, which is a problem. And on the other side, you have bioplastics on this corner. They are fossil-based, but they are biodegradable. They are driven by biomedical applications. So for example, for sutures in the body, where you try to fix something in the human body and you don't want to make a surgery 3 months after. So you need, for example, fibers which are degrading in the body within 3 months or 6 months. And this you can determine by the architecture of the material. So my favorite corner is upwards here, because here you have material which is bio-based and which is biodegradable in the end. And concerning a little bit the circular economy, or sometimes it's also called the circular bioeconomy, it is important that you don't see bioplastics only for single-use items or just throwaway items, but it's also important to think about bioplastics that they can be recycled, that they can be reused. So you need sugar-containing resources, sometimes in competition, perhaps to food. And so we have to think about this. But you can reuse it more and more and more. And only after a lot of uses, then you can dispose it or use the energy content. For example, when you use it thermally. Which means closing the loop is not only true for the normal traditional plastics, it's also important for bioplastics. Going a bit further, I have to show some chemical slides to get you a little bit into the topic. So how are these bioplastics are mainly produced? You can produce them by ring opening polymerization. So you have monomers like these ones. You have to break this CO bond in here. It's sufficient to break one, and then you can knit them together and form fibers, for example, in thermoplastics. And you do this normally with catalysts, and you're using a coordination insertion mechanism, which means here is the metal complex. The M is denoting the metal, and this metal complex is activating the lactide. Then you have here the first step of the nucleophilic attack to the ester bond. Here's the final step of the ring opening in event when the ring is opened, and so by this you insert into the metal alkoxide bond the lactide, and so the chain is growing. This is already done for more than 30 years, and industrially you do this with tin octoate. And the problem is this catalyst is totally cheap, it's highly active, wonderful, and so my story could stop here. But this catalyst is cytotoxic. We have done a lot of ecotoxicological studies with some biological colleagues from Aachen, and we found that this is in fact toxic. And in comparison, our complexes, which I will show in due course, are not toxic. This means if you are only dealing with some gram or kilogram of bioplastics, a little bit of tin does not matter. But if you think that about 20% of the plastics market can be exchanged by bioplastics, then the amount of tin catalysts being spread out into the industrial compost, for example, can be huge. I mean, it's not only a European viewpoint here. So for example, in Asia, in China and Korea mainly, and also in Japan, a lot of companies are now looking for alternatives because this tin octoate poses problems in the end, in the valorization, in the composting, and also in the recycling. So there are many catalysts in literature. I don't want to summarize them all. Beautiful, wonderful chemical systems, but the problem is that they are so sensitive. So they are active, but only under laboratory conditions, which means that the monomer has to be recrystallized 3 times, or it has to be sublimed. It has to be cleaned up, and that's a problem. So for technical applications, you cannot use them. And we are dealing in this topic for more than 15 years now. And our first catalyst 15 years ago, they needed 1 day for the polymerization. So they were active, they were robust because they are working with technical lactide, but they were too slow. I discussed with some companies and told me they need to be faster. Okay, and so we worked on many years and developed several generations of catalysts. So for example, going a little bit into the chemical detail, we are using zinc catalysts, and you can combine 2 guanidine units or 1 guanidine unit with an O donor. So here's an ester group again. You can play a little bit around here. So for example, you make some decoration here, which is again speeding up. So for example, this catalyst needs only 1 hour around. You can exchange zinc by iron. Still, it's not cytotoxic, and it's speeding up. So over the years, we have learned how to speed up our catalysts, speeding up in the polymerization process. And one of our fastest catalysts is shown here, which combines 2 of these bis-guanidine ligands. And in the end, as chemists, you have to prove that you have the substance which you are pretending. So we have, for example, the crystal structures of our complexes that don't go into the chemical details, but besides the synthetic data, how we synthesize the ligand, how we synthesize the complex, what's the structure of the complex. We also have activity complex. I can give you the slides later. It's all published. I also like open science, so no problem to give the slides to the organizers of the conference. And so what's important in our case is that we do not only do the chemical synthesis work, we also test the catalyst in the catalytic reaction. And herefore we have developed a reactor, which is a steel reactor where a Raman propad goes into the reactor. So we do the polymerization in the lactide melt at 200 degrees or 150, for example. So we can observe, for example, every second a Raman spectrum, and we can observe how this lactide band is decreasing because this is consumed, and how the polylactide is coming up, so how the polymerization proceeds. In the end, then you obtain a kinetics profile, a kinetic plot, and this proves that the kinetic is running in a ordered way, in a controlled way, and you can do lots of kinetics. This is too detailed in the moment to go into this. So just that to convince you, these catalysts are quite robust, they are fast, And they are about a decade more active than the industrially used tin octanoate, which is quite important. And they are not only fast in lactide polymerization, but they also work in the caprolactone polymerization. You can do this in bulk. You can do this in solution. So it's already a quite useful catalyst for a lot of reactions. You can also steer in the end how fast your material degrades. If you want to degrade it within months, or if it would, should take some weeks, for example, this can also be steered. But only making catalysts and doing the polymerization is only one part of the story. Meanwhile, we saw that it's also important to think about the bioplastics and the recycling of the bioplastics, because then you can use the material over and over in a cycle. And the problem is that in practice, you have mixed plastics. So we need a catalyst which is robust again. And just as an example, normally you would go in a linear way from the resources to the cyclic esters, come to the polyesters, and then it's done, go to the waste. You can degrade it, for example, but there's also the possibility to come from the polyesters to the alkolysis to an alkyl ester. And these alkyl esters, they are simple molecules, but in the industry, they are at the moment seeked as green solvents. So this would be an interesting valorization to come from plastics waste to esters as green solvents, for example, or you can also close up the cycle again, coming from the alkyl ester back to the cyclic ester and closing by this cycle. Meanwhile, there are also catalysts which are performing the reaction at high temperatures from polyesters direct to the esters. So back and forth would be also a possible way in recycling. Going a little bit more into the detail, if we see now the full value chain, then you have the possibility. So from the sugar, you come to the lactic acid, to the lactide. In the ring optimum polymerization, you obtain your polylactide. And here you can really perform mechanical recycling. But the problem is always if there is more than 5% of other waste in the plastics, then you are downcycling. I mean, we are all now downcycled examples where there is some plastics from old bottles, which in the end can be used as some floor coverage, for example, or as a bank, for example, but it's not really a true recycling. So there's also the possibility to perform the pyrolysis to obtain the lactide again, or also the alkolysis to come to the esters. And this is then used as chemical recycling. Some people also think that burning is some kind of recycling, so you can use a thermal energy content. I would not call it recycling because it's burnt. The material is gone at the end. And okay, from the CO2, you can go back to the plants. That would be a possibility. And for some years now, we are also testing our catalysts because many of the catalysts which are Lewis acidic enough to build up polymers are also able to break down the polymers again in the alkolysis process. And we tried to derive some kind of structural reactivity relationship, which means we had hoped that the most active polymerization catalyst is also the most active depolymerization catalysis. And for this family of catalysis is really working. So this is our winner in this case, in the small family. Because of this group, it has a high Lewis acidity, and the zinc is really important, activated for the catalysis. So this is a really good, fast polymerization catalysis. But in the end here, as black line, you also see it's also a fast methanolysis catalysis, also in the depolymerization of the polylactide to the esters. So for example, it's for the solvents. So in this case, the catalysts are obeying the order of the polymerization activity is also the depolymerization activity. I just put this point here because this is an example where it's working. If you change to the iron catalysts, it's not working. Our iron catalysts are faster in the polymerization, but slower in the depolymerization. So at the moment, we are investigating this with machine learning because we have so many catalysts now in my lab, which are active. And a lot of catalysts which are more active that we have to understand a little bit what is now the driving force for the polymerization speed and for the depolymerization speed. Going a little further, if you have now mixed waste, then you have the possibility, I go a little bit on, that you want to make a fractionated recycling, which means normally PET can be a little bit contaminated with PCl, or PLA is contaminated with PCl and PET. And in this case, we have a totally new catalyst, again, a ester guanidine donor. And if you play with the temperature, for example, at 40 degrees, you can use it to degrade the PLA. If you heat up, you can then degrade the PCl. And if you go to 100 degrees, then you can degrade the PET. And every time you can filter off the substrates, which is quite useful to make a fractionated recycling. But now I want to come to the point, how can we publish this in a fair way? And there is some problem which we have to tell about chemists. I mean, Udo has already named it. Sometimes chemists are a little bit conservative, which means in the year 1927, a lab notebook looked like this. In the mean, there was a lot of digital advantage, which means that in today's world, some iPhone has more computational power as the grade 2 in the 80s, which was really room filling. And this is now only a bag, small like a bag. But still in the year 2023, the most chemists, we made a survey, I think more than 70% are still working with pen and paper to document their chemical lab work. This is not digital at all. If we go a little bit further, in the lab, we are still working with paper and pen, many of us. Then in the corner, we have some terabyte storage disks. But in the analytical labs, we have wonderful, important machines, expensive machines producing more and more data. So in chemistry, the knowledge is doubling every 2 years. So we produce more and more data. But what do we do with the data in the end? In the end, we make nice NMR spectra, for example, or I saw in the other talk, for example, GCMS spectra or LCMS spectra, wonderful figures, and we put them as figures in the supporting information in a PDF. This is really boring data because they are not machine readable. These are just figures and no computer can really read them. Over the end, this means that the data are stored unfair. I mean, the FAIR acronym came in the morning already in this wonderful session, which means we have to make sure, in fact, that our data are published in a fair way, which means they should be findable, they should be accessible. So our data packets should have a DOI to find them again. They should be interoperable. I don't want to name any of these companies, but the problem sometimes if you measure an NMR spectrum with company A, you cannot read the data with a machine from company B. So you have a special data format, which is only readable if you have the software, which is expensive, by company A. So in the end, to come to fair data, you have to secure that you have fair data formats. I mean, in chemistry, there's a bunch of discussion about this now. And so we are going to be interoperable. And in the end, when all this is true, then it's also reusable. Within NFDI4Chem, our vision is to support the researchers for the whole fair data lifecycle, similar to what Udo has already explained. I mean, chemistry and catalysis are closely related. So with this means we are providing tools to process the data, to analyze the data, to preserve the data, publish them, and reuse them again to break out this linear process. And how we do this? Now, practically, for example, I showed you one of our fast catalysts. And in principle, normally, classically, you would just type all the data and publish it like this. This is not at all a fair way. But what we do now, I think I started later. So what we now do is that we put all our data in the so-called K-Motion repository. And in our publications, there is this classical data stuff because the referees are expecting this. But we also put all our original data in behind the link. And behind the link, you can come directly to the K-Motion repository. And behind the K-Motion repository, you find then full information, analytical information of our substance. So for example, you find the detailed data of our substance. You can find really the NMR data of our substance. You can also download them, which means it is fully fair way. And we do this now for 3 years with every of our publications, that every stuff which is publishable comes into the K-Motion repo. And everyone on the whole world can download this when having the link for free. It's fully free, fully open science in this field. And we also like this to teach this and use it for teaching in inorganic chemistry in Aachen for some years now. I will come to this in 1 minute. And someone tells me, if you don't have synthetic data, so no NMR data or RR data, but other data, then we have another repository, which is also free of charge. So for example, Radar4Chem, which is also, I think it's in Karlsruhe as infrastructure. And for example, if you think about our zinc catalysts, if you want to publish this data, then at the end we have a data availability statement, and there you have a DOI. And again, you can follow the DOI. You come to our original data. In this case, it's 50 megabytes of raw data. And you can follow again these data, download them, and there you find all the polarization data of all the catalysts at the different concentrations, for example, at the different equivalents. And here again, I want to point out that we have the free data format, the JCamp, because we can also use the data format of the machine, but then no one can read it. Besides, they have the same machine. So here it's again important to use free data formats. Going a little bit further, how do we use this now in teaching? In the end, we thought it's important to teach the next generations. And so, because I'm also the chef of an advanced inorganic lab course with more than 100 students every year, we decided to use the ChemOcean ELN as electronic lab notebook for the synthesis of the ferrocene in the lab, which means the students are doing the synthesis in lab, and concomitantly, they are also documenting all this in a digital way. And they really like it because now they see chemistry is going towards digital chemistry. And we support them, of course, not just that they type all the data in, but they also get short videos on the basics of RDM. What is a data management plan? What are the FAIR principles? What are metadata? And they also have to pass a small final test to be, in the end, convincing that they have not just cooked all the stuff, but they have understood what they are doing. That's also quite important. Going a little bit further, how does it look like? Just some glimpses of the ferrocene. They can really type and draw their chemicals. They can draw and write what they did. They can put their synthetic data, for example. And we also have tutorial videos on YouTube in German and English for all our students, so that they have a step-per-step description how this is using. So final message, teaching RDM and sustainability to the next generations, to our bachelor and master students, is really key to the cultural change to foster this on the long range, not just thinking about our graduate students, that's great, but also about the next generations. Finally, I want to thank all these funders who gave money for our research, but also the main partner, the main co-workers of the group who participated to this research. And you for your attention. Thank you so much.